Now we have input sequence. We have 3 time steps and 3 element vector. So we have 3 time steps x1, x2 and x3, and each has 3 element vectors, and we are just taking the initial state as 0 as 0 0 0 transpose. So we are representing each of these inputs x1, x2, x3 as embedding vectors z1, z2 and z3. And after that, our next task is to calculate the 1D convolution, that is also known as local mixing. So for that, what we will do, we assume that we have a kernel of size 3 with weight this. It is very important to know that we can fix the size of kernel as a parameter, hyperparameter, but we cannot fix the value of those kernels as a prior. This is a learnable feature in the Mamba architecture. Now again, there are two different kind of convolution we can achieve in the Mamba architecture. The first is causal convolution and second is non-causal convolution. Now suppose this is our element vector, and suppose this is a t and this is t plus 1, this is t minus 1, this is t minus 2. So in this case, so if we have a target, this is the target, and if we just move the center here, then we will be able to see the t plus 1 and t minus 1 both. So in this case, as we are able to see the next things also, so we will not be able to achieve the causal relations. So in that case, if we do such kind of element-wise multiplications to achieve 1D convolution, then our convolution will be non-causal convolution. But suppose if we want to achieve the causal convolution, here our value is t, this is our target, then we have to set our kernel in such a way that our right part of this 3 size kernel will be multiplied with stage 3, stage t. This is stage t minus 1. This will multiply with stage t minus 2. Means we will not move the kernel ahead from that state. So this is actually explained here. So in the causal convolution with kernel w1, w2, w3 mapping to vectors value w xt minus 1, xt minus 2, xt minus, so we have to do such kind of multiplications. And for non-causal, we are free. We can see the next token also. Now let us see some calculations for causal 1D convolution, that is local mixing. So here it is causal. So in this case, our kernel is this, and if we are at here at a time t is equal to 1, then we have to search for t minus 1 and t minus 2. As these things are not available, so we will achieve this through free states. So free states means all state value will be 0. So for x0 and x minus 1, all states value will be 0. So in that case, we have 2 0 0 0 states, and after that we will have states, this state, that is at t is equal to 1. So we will multiply this with this, we will multiply this with this, that is element wise, and we will multiply this with this. So here you can see that only this part is non-zero. So this is our output. And similarly for t is equal to 2. So at t is equal to 2, we will be here. Now we have a kernel size 3. So we will be able to see this part, and we have to take one free state. So here you can see that here one state is free and 0.2, 0.5 and 0.3 was value. Here by mistake got deleted. So and so here t minus 1 state is x1. So here you can see that 0.5, we multiply this with this part. So this is here, and this part with x2 at t is equal to 1. So we can easily get this value. Similarly for t3, if we are here, then we already have t minus 1 and t minus 2. So we will do that multiplication. And finally we get this matrix. So now we completed this page. After that, the next phase is state space model core computation. So before going into that, we will explain that we are using two different vectors. First is lambda and second is k. Both vectors are learnable vectors, and we already explained that lambda, it controls the memory retention, means old info, and k, it adds the new weights. And how it is learned by backpropagation. Both can be vector or matrix based on your data set. So you got the nature of lambda and k. Now we will try to understand this calculation. So calculation stage is also very simple. So at time t is equal to 1, you will be here. So in this case, your state as t minus 1 will be a free state 0, 0, 0. So when you will do the element wise multiplication with S0 to lambda, where this is the value of lambda, I have just assumed those values to show some calculated results. So in this case, this part will be 0, and for this part k equal to 1, 0.5 and 0.2. So when we multiply it with st, current t is equal to 1 value, that is z1. We can also say it like z1, this is z2 and this is z3. So when we multiply this, apply the element wise multiplication, 1 with 0.3, 0.5 with 0.0 and minus 0.3 with 0.2. So we will get this score. One important thing that you can easily see here, the value of 0.8 is very good. This means when we multiply this value with some good value in the 1D convolution output, then, or sorry, when we multiply this value with some of other values, then chances of retention of that value will be high. And for 0.7 it may be little less, and for 0.6 it will be moderate. And similarly for k, if we multiply any value with 1, the chances of additions of that value will be very high. If we multiply it with 0.5, the chances of addition of new value will be 50-50, and 0.02, it will not be added. Now just to take the at t is equal to 2, so you already know that t is equal to 2, this is z2, that was our z1. So we multiply lambda with our s1, that s1 is our z1. So when we multiply this value with this value, element wise multiplication, like this with this, second with second and third with third, and similarly with this k and z2, we will get this value. Similarly at time t is equal to 3, the state space model core memory management value will be here our S3. So we will multiply lambda with our S2, that is our t is equal to 2 value, that is our Z2 value also. So we multiply here, and similarly we can multiply k with Z3 or S3 and sorry Z3. Then we are getting this value. Now here I have just covered all those values through simple matrix. So local mix means after this 1D convolution at time t is equal to 1 we got this value, time t is equal to 2 we got this value, and time t is equal to 3 we got this value. And we had states that is called value that we are getting from this part. Like here we got 0.2, 0.272, 0.205 like that. So we already got this. So this is state output, and after that we are using some multiplicative bias gate that we already discussed. This is a perceptron architecture with sigmoid activation. So suppose this is our learn gate output. So in that case we will calculate the gated state output. So this is known as multiplicative bias. This decides which part of the memory, which of those learned memory or which of those stored memory we will continue for the next phase. So for that, at time t is equal to 1, we will use the state S1 output. So this is state S1 output. We will multiply it with G1. This gate 1, state S2 output with G2, state S3 output with gate G3, and finally this type of output we will get. Finally, this type of output we will get through element-wise multiplication. So here this is S3 value. So finally we will get the S1, S2 and S3 output, and after that our task is output projection. So generally we use the linear output projection. Linear output projection. So in that case, so in the case of linear output projections, we just use the same value here as a final output. So now you are able to understand that this was our input for which we got this output. For this input, we got this output. For this input, we got this output. So here you can easily imagine that how the system behaves and which of the part of information is used by the system in generating the specific patterns from the data. And those patterns you can apply the multiple stack of such kind of a complete Mamba architecture, multiple stacks of such kind of Mamba architecture to develop some applications. So based on like how many stacks will actually useful in to achieve your goal, you can fix the Mamba stacks. And after that you can use the output for classifications, for regression, for sequence predictions, or for any other tasks. So this is the complete information about the Mamba, basic vanilla Mamba architecture. Next time I will explain more mathematical rigor about Mamba architecture, and also explain a lot of advancements in the Mamba architecture.